Hello. In the last lecture, we described what is breadth first search, and based on that, we developed an algorithm to compute the shortest path from a given vertex x to each vertex of the graph. And the algorithm is reproduced here. The two important features of this is every vertex v for which we assign the parent and the d value is one which is unvisited. At that time, we reassign the status to be to be current. So, every vertex has only one assignment to their d value and to their parent value. We also stated one claim and proved it, that every vertex enters and exits the queue precisely once. Now, we will go on and prove the correctness of this algorithm. That is, we will establish that indeed it computes the shortest path tree for vertex S. So, let us define a notation we state that vertex u precedes vertex v to mean that u exited q before v. Now, that is because every vertex actually enters and exits, and that is exactly once. So, there is a natural order in which these vertices are exiting from Q. So, this is a well defined total order on the vertices. Now, we are going to state an important claim. That is, if vertices u and v coexisted q and at any time, rather at any point in time and u was ahead of v, then d of u plus 1 is greater than equal to d of v, which is greater than equal to d of u. So, let me explain what I mean by this claim. Let us suppose, so let me write down here that this represents the queue where the elements exit from this end, and at some point in time u was somewhere here and v was after it. So, the claim says that the value of the d value of u and d value of v, their difference cannot be more than 1, and this cannot be less than the d value of this. So, we will prove this claim by induction on the iterations. So, initially let us take the state when we first enter S or we NQ S into the queue. So, initially you have only one element, namely S. There is no other element. So, the claim is trivially true. There is nothing to compare with. So, let us suppose, so initially naturally, so it is trivially true. So, we will take now an induction step and suppose after I minus 1 iterations, the claim holds. So, I would like to prove that the same holds after ith iteration. So, let us suppose we have this situation. At the head of the, this is the direction of the queue, at the head of the queue is vertex w, and then we have other vertices, let us call them x1, x2, x3. At the start of the iteration, as the algorithm does, it picks the element at the head of the queue. So, that variable stated to be u is this vertex, has value this vertex w. So, the w has been taken out, okay, this is taken out. Let us come to that piece of the code when you are taking the u out. So, w is this vertex, and now what you do is you look at all the adjacent vertices to the selected vertex w, and what you do is you assign the d value of each of these neighbors to be 1 more than the d value of w, provided it is not already visited. So, it is unvisited. So, when we take out and suppose this is vertex w and you have several neighbors to this, say y1, y2, y3 in the graph, and if these are new vertices, unvisited vertices, then we enter them here. So, y1, y2, y3, they start entering into this, and their d values will be 1 more than the d value of this. So, the d of y1 and d of y2 and d of y3 etc., these are all d of w plus 1 more than that. Now, from induction hypothesis, the d value of all of these cannot be more than dw plus 1. So, after this iteration, what you get here is x1, x2, x3 etc., then y1, y2, y3. Of course, those vertices of w which are current, they are already present in this, so we do not touch them, but the other vertices which are unvisited, they are entered into the queue and their d values are dw plus 1. So, now the d values of all these vertices is between dw and dw plus 1, and the d value of these is exactly dw plus 1. So, our claim is that for any two vertices, if you take any two vertices, say you pick any vertex here, any vertex here, then the d value of this is greater than equal to this and the difference is at most 1. Now, if both of them are from this collection, that claim was already true, because the claim was true in I minus first iteration. If the second vertex, the second vertex is among these y's, then we know that the d value of this is either dw or dw plus 1 and this is dw plus 1. So, once again the difference is at most 1, and this is greater than equal to this. And if both of them are, so if we take this off and both of the vertices are from this set, then their d values are same. So, the claim remains true in all the 3 situations. Hence, the claim has been established by induction. So, one of the consequences of our result is that the d value of every next vertex cannot be less than the d value of the previous vertex. So, a corollary to this claim is that if u came out of the Q before V, then the d value of u cannot be greater than the d value of V. Okay? So, the second thing that the second thing I would like to establish is that every time we assign a d value to a vertex which was in the neighborhood of u, we establish u as its parent, and d value is incremented by 1. So, what happens is that suppose this is V and this is u, then this has some d value alpha, then this has d value alpha plus 1. Now, when u was assigned value alpha, it must have been assigned a parent, let us call it x1, and the parent's d value must have been alpha minus 1. So, if you go backwards, every vertex except S has a parent, so it will reach S and its d value is 0. So, what you notice is that just by walking along the parents of the vertices going towards S, we find that we build a path from S to the vertex, and the d value has to be the length of that path. The reason is that every time we walk along one edge backwards, we reduce the d value and it reaches 0. So, the d value is the length of that path. So, we can also claim 3 is that there exists a path from S to V with length dV for each vertex V. This implies a corollary is that d of V has to be greater than or equal to delta S V for all V. Let me remind you that delta S V stands for the length of the shortest path from S to V. Among all paths from S to V, the path which has got, or those paths which have got the minimum length, their length is this, and this is the length of some path from S to V. So, this has to be less than or equal to this. So, now we want to prove the main result, that not only that this is greater than or equal to this, but we will establish that this is equal to this, that dV actually computes the shortest path from S to V. So, let us try to do that. So, next claim 4 is that for all v. How do we prove this? So, we will prove this again by induction, but this time we will do induction on the delta value of that vertex. Each vertex v has a delta SV value, unique value, and we will prove this with the increasing value of delta. So, which vertex has got the minimum delta value? Exactly the value of S, namely delta SS is 0, and the d values can never be negative, because the only thing we do is we assign the d value of some vertex plus 1. So, there is no reason for d value to be negative. So, it is the least. Okay. Now, so this is by induction on delta SV. So, the base case, as we said, is when delta SV is 0, and this is true only if V is equal to S. The d value of S is independently set to 0, well, it is set to 0 with every vertex V, and d value of S is never changed. In the entire algorithm, the d value of S is never changed. So, it remains 0. So, indeed, for S, this claim is true. D of S is 0, delta of SS is 0. So, base case is correct. So, now we want to prove for other vertices. Now, so for induction step, we will take any vertex V and will take a shortest path, namely so let us say this is a shortest path from S to V. In general, there could be more than one shortest paths. So, I picked one of them. The length of this path has to be delta SV by definition. Let us say this is K. So, induction hypothesis is that the claim is true for every vertex V for which delta SV is less than or equal to K minus 1. So, the induction hypothesis says d of V is equal to delta of SV for each V if delta of SV is less than or equal to K minus 1. This is the induction hypothesis. And now I have a vertex which has delta SV value equal to K. So, we would like to prove that d of V is K, then we are done. So, how do I show that? Well, the d value, observe that d value of x1, which has to be delta value of Sx1 is K minus 1. This is the first vertex from this end on the path, namely x1. This is x1. This is K this is k minus 1. Why is it k minus 1? Because if there was a shorter path from S to x1, that is, if there were a path from S to x1 with length less than x1, then I can replace this path by that shorter path, and then I will get a path from S to V of length less than k. That is not possible. This is the shortest path. So, each subpath is shortest. If delta V x1, delta S x1 is k minus 1, then from induction hypothesis the two are equal. Now, because the d value is equal to this, so when we expand the neighbors of x1, that is when vertex u in the step 5.1 was x1, then we were looking at the neighbors of x1 here. If it was unvisited, that is, among these we had this V vertex here, which is one of the neighbors. If it was unvisited, then I would have assigned the dV to be du plus 1, which is k minus 1 plus 1, which is k. Suppose this was not unvisited, which means it was visited earlier. So, the parent of V came before x1 came. Okay. The second situation is, while expanding at x1, we visited V and we found that V was not unvisited. So, we must have been visited through some other vertex. So, the parent of V occurred before x1. So, we know that parent of V is either x1 or it came before x1. In that case, the d value of u, d value of V. So, d value of V is less than or equal to d value of x1 plus 1. We have proven that. If so, the vertex that comes earlier, its d value is lesser or equal. So, d of V is less than or equal to dx plus 1, which is equal to, which is precisely what? K minus 1 plus 1, which is k. So, we established that dV is less than or equal to k. But take a look at this claim. dV can never be less than delta of SV, and delta of SV is k. So, putting together, we conclude that this is saying dV is less than or equal to k, this is saying dV is greater than or equal to k, hence dV is equal to k. So, we have proven that dV is equal to delta of SV for V as well. Okay, so, we just proved that dV is equal to delta SV, the shortest path length from S to V, which is also the distance of V from S for every vertex. We also proved that there is a path from S to vertex V of length this. Hence, we have, and that we can build by just tracing the parent, going from vertex to its parent, to its parent's parent, and so on. So, we can, from this information, we can deduce that path. Okay, as we output here the graph for this vertex set, we set those edges which are from vertex to its parent, and for every vertex other than S. So, we have all the information in this graph about the shortest paths. So now let us take a look at the time and space complexity, right. So time complexity in this algorithm, these 3 steps 1, 3, 4 are all constant time, and this one has got some constant number of operations, it runs over each vertex. So this is of time order n, where n is the number of vertices. Okay. Now let us take a look at this while loop. Well, this is a constant time. What will dominate is this for loop. In this loop, we notice that for each vertex u, we do this once. Remember that each vertex enters and exits the queue. This is the time when this u has exited from u. We do this process. So what is the time complexity of this process? Well, in this we visit each neighbor of v and then check whether what is the status, whether unvisited or it is otherwise. And depending on that, we do some constant time operation. These are 4 fixed operations. So for every neighbor of u, we will do once. So what we have here is that some C1 n for the step 2, and then for step 5 we perform for every vertex u in this thing degree of u time operation, some C2 time. C2 time. Degree stands for the number of vertices which are adjacent to u. For example, if you have a graph such as this, and this is u, then 1, 2 and 3 and 4. There are 4 vertices adjacent to u. The degree of u is 4, degree of this vertex is 2, degree of this vertex is 3, the degree of this vertex is 3, degree of this vertex is 4, and so on. So that is what degree stands for. So this is the dominating, these are 2 dominating terms, and everything else is of course in constant time. So, well, this is really not constant time, this is also order n. The reason is that you, I am sorry, this is not even order n, this is the number of edges in this graph, that is the time complexity, number of edges that we have. But number of edges are what? For each vertex there is one edge. So it is actually n minus 1 such edges. So this entire thing takes order n time, so which is already accounted for. Now what is this term? The sum of the degrees of degrees of the vertices of a graph. If I just sum this up, I will get 2 plus 3 5 and 4 9 and 3 12 and 3 15 and 3 15 and 3 18. So we have 18. Number of edges in this is 1 2 3 4 5 6 7 8 9 10 11. So I have missed something, let me add up again. 2 plus 3 5 and 4 9 and 3 12 and 3 15 and 3 18 and 4 22. So the total sum is 22, which is twice the number of edges in it. in general you can easily show that the sum of the degrees of the vertices of a graph is 2 times the number of edges, and that is simply because when you count the degree, you count for a given edge, you count it twice, one at this end, the other at this end. Hence, the sum turns out to be 2 times the number of edges, and m denotes the number of edges in the graph. So, this time complexity is order n plus n. The space complexity note that the major data structure we have used here is the adjacency list, in which what we do is for every vertex we store the list of all the vertices which are adjacent. So, for you we must have stored in a list this vertex, this vertex, this and this vertex. So, the length of the list for u is exactly the degree of u. Hence, the total space used is the sum of the degrees of the vertices, which is m, 2 times m. So, the data structure called adjacency list takes order n time, m time, and we have certain lists like parent and D and all that, which take order n space. Status also takes order n space. Q, the size of Q in the worst case could be order n, the total number of vertices. So, all the set of lists that we see here take order n space. So, this is also order n plus m. So, this completes the discussion of our algorithm. We have proven the correctness and we have found the time complexity and the space complexity. Now, so far what we have done is we have assumed that we have a graph for which we can compute the shortest distance for every vertex from S, and what we output also gives you the path that gives such a one path which gives you such a distance. Now, as we said, if you take every vertex and go back to its parent and go on, you end up into S. Maybe some of them are already there. So, if we start building this, what you will build is a tree, and the length of the paths in the tree from each vertex to S is precisely delta S v for that vertex v. So, this is indeed the shortest path tree, but there are certain things we have ignored. So, the question is, what if the graph is not connected? So, what do we mean by that? So, what we say is that let us suppose the graph looks like this. This is the graph. Turns out that the set of vertices here which have no edge to this set of vertices, which means there is no way we can go from S to any of these vertices. Such graphs are known as not connected graphs. If I input such a graph to our algorithm, what will happen? Well, it is clear that after this algorithm is complete, none of these vertices will figure in this. Their D values will never change. The parent values will remain nil. So, their D values will be 0, which is incorrect. The d value of only s can be 0. In fact, what typically one states is that the d value of these should be infinite to indicate that there is no path from S to this. So, we should ideally initialize the d value to infinity rather than to 0. So, we should actually set dV to be infinity. That way, if any vertex not accessible from S is there, then its d value will remain infinity. We will have to make one more addition to this, because d of S must be 0. So, we should say that d of S is 0 separately. That is the only change we need to do to handle the graphs which are not connected. But we will have to now change the definition of shortest path tree. Earlier what we said is that it is a subgraph of the given graph, which is a spanning tree, which means that every vertex is present on this tree, and the shortest path from S to each vertex in the graph is also equal to the distance from that vertex to S in that tree. In a tree there are precisely, there is one path between any pair of vertices. So, what we notice here is that in general, if the graph is not connected, such a thing is not going to happen. Okay. So, what we will do is we will redefine the notion of shortest path tree as follows. So, definition is that for a graph G equal to V comma E and a given vertex S in V, the shortest path tree is a subgraph T, which is a tree and contains all vertices which are reachable from S. And del G S x is equal to del T S x for all x in T. So, we define the notion of reachability. We say that a vertex is reachable if there is at least one path reachable from S, if there is at least one path from S to that vertex. So, all these vertices are not reachable, all these vertices are reachable. So, our definition is that this shortest path tree is a tree indeed, it is a subgraph of the given graph, which means its edges are from the edges of the original graph G, but its vertices are only those vertices of G which are reachable from S. So, it will be only restricted to this part, and the other part is the same, namely that the distance, the distance which means the length of the shortest path, the distance of each vertex from S is in G is same as the distance from S to that vertex in T. So, with this definition we can handle the non-connected graphs as well. Now, we will define one more type of graphs which are called directed graphs. In these graphs, we have same thing, set of vertices, set of edges, but these are directed edges. In other words, for any pair of vertices u v, if there is an edge, we also assign a direction. So, we say the edge is u v to indicate that edge is between u and v and its direction is u to v. So, in general u v is not equal to v u. Besides, any of these can exist or may not exist. So, it is possible that you have a situation like this, or you have just one edge in one direction or the other. All these are possibilities. Okay. This is same vertex u v. In this situation, we modify the notion of path in the following sense. We say there is a path from x 0, x 1 all the way to x n minus 1 and x n. But now we also insist that the direction of each of these edges is going away from x 1. So, all of these are directed in one direction from x 1 to x n. So, you may have a path from x naught to x n. That path does not become a path backwards. So, this is not a path from x n to x naught. Now, let us take a simple graph. Now, the direction of the edges, I think it is not that clear. Let me just make it cleaner. X 3 is this vertex. If you notice, the paths from S manage to reach x 1, they can reach x 2, they can also reach x 3, but there is no path from S to x 4. So, the notion of reachability now generalizes further in this case. We say that in the directed graphs, a vertex V is reachable from S if there is a path with appropriate direction. Here the reachable set is S itself, x 1, x 2 and x 3, but x 4 is out. So, in the output, if I run this algorithm exactly as it is, in the output x 4 will not figure. The d value of x 4 will remain infinite. So, when we have a directed graph and we input that graph into this algorithm, what will come out will be some structure such as this. And so on. it will describe set of paths from S to every vertex, which are shortest paths. So, we can call this a rooted directed tree. Rooted to indicate that there is a special vertex in this, we could call root of the tree, and all the edges are pointing away from the root, and all these paths are appropriate directed paths, and they are the shortest paths. So, the algorithm functions exactly the way it did in undirected case, but this time it will contain only the vertices which are reachable in directed sense. Now, the last thing I want to describe is edge weighted graphs. So, edge weighted graphs can be expressed as this triple. This is again set of vertices, set of edges. Now, we are talking in terms of undirected graphs, but we have a third entity which is a function. In this context, we are defining these functions as functions which assign a non-negative integer, which we call weight, to each edge. So, we can think of such graphs as 2, 7, 8, 4, 9, 12, 14, 4 and so on. So, such a graph is an edge weighted graph, and given this, we can again define the notion of the weight of a path. So, something called a weighted path length. So, suppose you happen to have a path 4, 7, 2, the weighted path length is nothing but 4 plus 7 plus 2. Unweighted path length was 3. So, it is 13. The distance, the weighted distance from, let us say, a vertex S to V, which will denote now by is the minimum of the weighted path lengths of all paths from S to V. So, we have the similar parallel notions. Earlier we had shortest path length or the distance defined without worrying about the weights. Now, we just take into account the weights. Okay. And once again, note that if you have a path, okay, let us say x1, x2, x3, x4 and so on, with weights alpha 1, alpha 2, alpha 3 and so on. If this is the minimum weight path from this vertex to, let us say, xn, then any subpath, you pick any two vertices, this has to be the shortest weighted path between these two vertices. If it was not, then I can replace it, and if it adds some cycles, you remove those cycles. and you can find a shorter path, lesser weight path from x1 to xn. So, that is still there. So, the final thing is, because of this property, there is still a well defined shortest weighted shortest path tree from every vertex. So, we can say that there exists so claim is without proof, but the proof is very similar. Without proof, we can say that for any weighted edge weighted rather, for any edge weighted graph with W going from E to R plus, this is to indicate that negative numbers are not allowed. There exists a shortest, weighted shortest path tree for each S in V. So, in the next lecture, we will describe how to compute this, and we will do that by modifying this very algorithm suitably.